Okay, so today I'm going to be talking to you about three general areas. The key topics are talking about established data science projects, talking about experimental data science projects, and then talking about the key differences between these two projects and talking about how that is going to be different to any of the other projects which you guys work on a relatively common basis. What is beyond the scope of today's discussion is what is data science? What is an actual data science model in terms of the nitty-gritty depth and detail of what these things are? What is data ops or deployment and deployment ops? How you gather data, how you manage data lakes, how you manage feedback loops and automated retraining. So the exact science of data science, the exact methods of data science is beyond what we're trying to talk about today. Now, that being said, do not worry, do not have concerns. If you don't have a grasp of data science or you don't understand the technologies behind it, don't worry, you don't need that to understand what I'm going to be covering off over the course of today. But before we go any further, what I'd really like to do is start off with just a baselining a few of the key terms and a few of the key contexts. First off, we have data scientists. Now, data scientists are the people who are responsible for analyzing, interpreting, and the processing of extremely large sets of data. They are also responsible for identifying patterns in that data and using those patterns to create computational models that underpin the actual machine learning itself. Next, we have the ML engineers. Now, the ML engineers are specialist software engineers that are skilled in the integration of those data models that the data scientists produce. Their role includes data handling, model output interpretation, and the development of UI that presents the outcomes of those modeling processes. So actually taking what is output from the model and presenting it on the screen in a way that is usable. There are lots of different ways that these ML engineers are described. Sometimes they're called ML engineers, sometimes they're data engineers, and sometimes they're AI engineers. But for the purpose of today, I'm going to blend over the very small differences between those different groups and refer to them all as data engineers. Nextly, we have machine learning. Now, machine learning has become the more accepted name for artificial intelligence. Following on from a series of films that have pervaded since the mid-80s, where machines have developed their own intelligence and sought to take over the world, there's been a bit of a swing away from terms like artificial intelligence and more towards machine learning. But machine learning covers all forms of machine-based computation. So that's machine learning or natural language processing, optimization, and prediction as well. Next, we have the computational model. Now, a computational model is the part where the machine interprets and learns. In fact, it is the intelligence part of artificial intelligence. Technically, a model is a code-based representation of a mathematical model that is used to interpret complex nonlinear systems. It can often be thought of really as a network of micro decisions that, when all those decisions are taken together, delivers a single conclusion with a certain level of confidence. And that conceptual model is very much the way we understand the way in which the human brain operates. A series of individual nodes which make parts of a decision, but when connected together, produce an entire decision. And this is modeled as far as is humanly possible within these computational models, within this machine learning environment. Normally, it's usually referred to as just a model, and that's what I'm going to be calling it as we go through the course of this presentation. Let's take a look at the two key areas. So first off, we have established data science. Now, when we're working with established data science, we are working with commonly seen problems. We're often using commercially available models that can be bought from the likes of Google or or other similar companies that are starting to get into the artificial intelligence and machine learning world. And they are developing their own models that can be bought off the shelf and are ready to use by individual companies that don't necessarily have a specialist data science division, or they do have a data science division, but they want to bypass the need to produce their own data models by using ones that can be bought in. But because they're bought in, because they're sold by typically quite specialist companies, those models come in pre-trained and are highly, highly accurate. In that respect, they can be kind of considered more akin to an engineering framework, where you bring in a framework and you cherry pick the parts of that framework that you want to combine and build to make an application. In the same way, you can go to companies such as Google, such as Amazon, and buy these pre-trained models and use them as you see fit, either as they are or adapt them to your own requirements, or indeed build them into your own systems and your own applications. On the other end of the scale, we have experimental data science. Now, experimental data science is where we're starting to use new or emergent models. Very often they are research-based in nature, either in terms of the project itself or in terms of the models that you're using. And this means they are more likely to follow a scientific method rather than an engineering method. Now, as such, you see, although they typically involve an awful lot of research, development of hypotheses and experiments to prove or disprove those hypotheses, and then high levels of refactoring before you repeat the whole process again to develop more knowledge and more capability. Very often, when we're dealing with experimental data science, we're dealing with environments that have close connections with academia and the interpretation of recently released white papers from those academic bodies. In essence, it means that we are developing new models, or indeed, we're working with typically unproven models, or sorry, hitherto unproven models. And this means that when we're dealing with experimental data science projects, we're working in a highly experimental way. And from an agile perspective, that means we're actually relatively unpredictable. So we end up in a position where experimental data science is very good for complex data and complex problems, and established data science projects are much better at handling common problems and better known problems. So let's take a look into how we can work with established data science projects and how we can operate in these well-known ways. First off, as I said before, established data science projects are very good at working with known problems. So very typically, they operate using data science models that focus on facial recognition or voice recognition or natural language processing, perhaps machine vision or character recognition. The kind of places where you see this is biometric security. So when your phone does facial recognition to let you in, well, that's actually an AI system, a machine learning system that does that. When you start talking to service providers on your phone and they say, tell us your answer now. Here are 5 options. Do you want option 1, 2, 3, 4, or 5? And it listens to you. That's voice recognition. When we're talking to Google and we're putting our questions in, that's natural language processing. There are obviously other forms of data science and machine learning models out there. When you go to Netflix and you look at the Netflix screen, you are actually looking at a screen that's bespoke tailored to you, and it's being bespoke tailored to you using machine learning systems. It looks at what you do, what you're watching, what you're interested in. It identifies the patterns in that data and then uses those patterns to make recommendations that it believes you would like to use. But this is still solving a known problem. Now, because it's a known problem, we're dealing with a system whereby the models can come pre-trained because the systems are relatively common, the questions are relatively common. They are ready to use when you buy them off the shelf. They can be easily optimized by yourselves for whatever point and purposes you need within the confines of the problem they're trying to solve. And as a result, they're actually more easy to use and are relatively commercial from that point of view. But because they are well known, and this being the big advantage, they are operating with well-known problems, they're also highly predictable. And that's probably one of the strongest advantages of using this sort of system. They are highly predictable. Not only are the models likely to behave in predictable ways and give predictable outcomes, but the data scientists are also able to give estimates for the durations of their work. That means they can say, in order to integrate this piece of machine learning, it is likely to take me a certain amount of time. Or indeed, if they want to start interpreting those outputs or tweaking or changing the way the model works, then they're able to give more accurate estimates, or at least relative estimates that we as Agilists are able to use to help understand how much work a data scientist has to get through, and fundamentally, when a given piece of work is likely to be done. And this means that Scrum works. That degree of predictability, that degree of capability to estimate means that everything that we do with Agile Scrum actually fits very well. We have a backlog of work. That backlog can be sliced down. The team can give relative estimations. We can have vertical stories that span all parts of the system, from the front end through to the back end, through to APIs, through to the data science. We're actually able to develop and build on user stories and deliver those. And that means we can also do sprint planning, and we can estimate how much is going to be done and use burn down charts as well. We have regular collaboration and the regular demonstration of value to our customer. Scrum works under these circumstances, and it's actually a very natural fit. Now, that being said, there are a couple of key elements that we need to be very aware of and to bear in mind. First off, models need data. It sounds fairly obvious, but I've worked on a vast number of projects where where the data just wasn't available, or it didn't become available until quite late on. And the data scientists will need a data phase to analyze that incoming data so they can organize it into such a way that the model can use. If you don't have the data, you can't organize it. If you can't organize it, you can't feed your model. If you can't feed your model, you will not actually have a model that can interpret an output. And the next thing we need to be aware of is what our agreed accuracy targets are. Now, the accuracy targets we'll talk about a little bit later, but fundamentally it is about how well the model performs. So once we've got our data, once we've got our model, we can merge those two together and we can set the model up to be able to do the analysis that we're asking it to do. But we need to know how well it's doing, or how well it's performing, or how well it's actually doing something that we're asking it to do. Let's say we're talking about facial recognition. Well, if you're talking about facial recognition, a relatively high level of accuracy is probably required. If it was on your phone, you need sort of 80, 90, 100% accuracy. There's no point having a facial recognition system that doesn't recognize a face most of the time, especially if it's you and your phone and you can't get in because it doesn't recognize your face. However, if we're talking about facial recognition in a slightly broader context, where perhaps a police force is analyzing a crowd, then we need to start talking about a lower level of accuracy, so you can scan a wider number and get a wider number of hits, and then the human person can be involved in saying, yes, this person matches what we're looking for, or this person doesn't. I'm obviously avoiding the morality and the moral suggestions that such a facial recognition model would bring about. I'm just using it purely for a discussive purpose here. Once you've worked out what your targets are, you then need to have a plan to recognize drift and retraining. And again, we'll talk about that a little bit more as we go further through. But the general premise is that as a data science model goes through its lifespan and gets older and older, it's likely to be less accurate and needs to go through a period of retraining. So understanding how that operates and how that will impact in your data science model is a critical element as well. And the last thing we need to be aware of is siloing. It is really, really, really easy in a data science project to end up in a position where we are siloing. It's a very, very real very real risk. And the reason it comes about is there's a bit of a mindset where a data scientist says, I'm going to build my model, I'm then going to pass it to an engineer, and the engineer will integrate it. The engineer takes the model and integrates it, builds the front end, and then passes it to the QA. The QA has to test it and can only test it when both the model and the engineering piece are combined into a working system, and the QA is able to test it and say, yes, this does, or this does not work. And in this way, it's really, really easy to end up in an isolated, siloed, Agile approach, even though we're still operating under Agile Scrum, even though we're still doing estimations, even though we're all still doing sprinting, even though we're all still doing regular deliveries at the end. So it's very important to recognize that that is a very real risk. And this approach also reduces the speed with which the value can be delivered quite dramatically. Now, that puts us in a position where value is being delayed not through the team operating in a bad way per se, but because they're operating in a way in which they think is right. And that's a drift in alignment of their activities. So rather than everyone working on a single feature at the same time, we end up in a position where the data scientists are building their models, or they're working their models, and they're saying they're not quite ready for integration yet. So the engineers are just doing their thing and getting as far as they can while they wait for the model to be delivered. And this can often be traced back to non-user centered stories. That is, stories that don't say something along the lines of, as a facial recognition system, I want to recognize a person's face 70% of the time, and actually having stories that are more technical based in nature or more data science based in nature. And when we're dealing with quite high-end, technical, cutting-edge systems such as these, it's actually very, very easy to end up in that position. And through that, we end up building those silos, and we end up in a kind of a waterfall position. And so very, very quickly, we end up in a position where someone says, hey, let's set up some fake data. Let's set up a system where we are able to continue our app development, continue our model development, but have a layer of fake data in between, which allows those two to operate in a desynchronized fashion, and everything kind of goes back to a more sprinty, scrummy kind of way. But we've got this fake data layer to bridge the gap where one of the two elements isn't ready for delivery, but the other is ready to receive. Now, we have to be super, super careful about that. Being in that situation. And the reason we have to be careful of it is fake data is by its nature fake. When we operate in a software engineering scenario, fake data isn't necessarily going to cause us a problem as long as it's of the right sort and the right type. When we're in data science environment, fake data can actually kill us. I remember a project I worked on a while back, which was to recognize the activities that people are conducting in a given industrial site. So not with members of the public, but in a closed environment where we're only dealing with employees. And we had a series of cameras that were set up to be able to recognize the comings and goings of the members of staff. And we were, on the one hand, working to understand what they were doing to ensure they weren't working in an unsafe way. And on the other hand, we're also using facial recognition as part of a security measure to ensure that only authorized people were operating in a given area on an industrial site. Makes a lot of sense. So the data scientists early on found they couldn't get access to the live data because, again, of that security system. It was a closed circuit system where there were no outside links. So instead they set up cameras on their desk and they started using their own faces, looking at the cameras to see if the system could recognize them. And they were getting a very high level of accuracy and were very, very happy. The thing is, that was effectively fake data. It was not the real data. We were bridging that lack of data to allow the system to be up and running much, much faster. When we got into the real world, we found that the cameras were 15 feet up on a 45-degree down angle. And not only on a 45-degree down angle, all of the people had their heads facing on a 180-degree, 0-degree plane. And that meant the camera was looking at the top of the head rather than the front of the face. And suddenly the whole system failed. We actually weren't able to recognize anyone at all, and we needed to completely rebuild the models and completely retrain them using a slightly different angle on the face. Not only that, because the industrial unit was outside, we also had to contend with different lighting levels. We had to contend with different environmental systems as well. So rain, cloud, bright sunshine, low sunshine, snow, and so on. And that meant that we were in a situation where a model that had been developed and was essentially working in our office environment suddenly wasn't working when we went into a live environment, and it wasn't working because of fake data. So if you are ever going to use fake data, if you are ever going to use these systems to try and enhance the speed with which you can develop, be aware of the quality of your data. More recently, I've been working on a system where we did need to use fake data for almost exactly the same reason. So instead, we got an extract of live data that was 6 months old. And we went out our way to make sure that we had that data and that we could use it for training purposes and for the purposes of making building the system such that it could move through our development much, much faster. But because the data was in effect real, it just wasn't current, then we were in a very good position. We could deliver effectively. But that awareness of the quality of the data and the impacts of fake data was critically important in terms of us being able to get on and to be able to develop a system that was effective. So that's everything I particularly wanted to say about working with established data science in an agile way. But just to summarize it, very often they are bought in and they are pre-trained. They are designed to solve common problems. They require a database to gather the data, make sure it's in the right form and format, and it can be introduced into the data science model. Scrum works without any significant degree of change. Be aware of fake data, and that between fake data and Scrum, we can end up in a agile, siloed situation relatively quickly. And above all, set those accuracy targets so you know when your model is reaching a performance stage. So moving on from there, I wanted to spend a little while talking about experimental data science. Experimental data science projects are not the same as established data science projects. They're in fact very, very different, and treating them the same will often lead to problems. In fact, many of the issues data scientists, businesses, and agilists have stem from this one misunderstanding. And it's a critical understanding to have. And any time that I've worked with projects or worked with people or spoken to data scientists or agilists who are having challenges in the data science environment, it very much comes down to this statement. The two types of projects are actually different, and you cannot treat them as the same. So just to very, very briefly recap on what those differences were, we've just heard about the established data science, so let's talk about the experimental stuff. So I'm just going to repeat what I said more or less earlier. They use new or experimental and emergent models. They are often very research-based in nature, and as such, they tend to follow a scientific process. And that means there's a lot of research, development, production of hypotheses, experiments to prove or disprove those hypotheses, and then a high level of refactoring to be able to develop more knowledge to work on. Very often there are close connections with academia, and that means that we are working with or implementing recent white papers. In essence, we are going to be working with new, emergent, or very cutting-edge models, or indeed we might be working with totally unproven models. And because of this, and because of the experimental nature, it means that from an agile perspective, we're actually in an unpredictable situation. That being said, experimental data science is very good for complex data and very good for complex problems. As the name implies, data science begins with data, and actually so do our projects. Before we begin a project, especially the experimental ones, we need to ensure that our data is fully prepared and ready for use. There are far too many projects that I'm aware of that have begun by diving straight into development, but that can cause a number of issues. Preparing the data up front can save a lot of time and a lot of challenges. Now, the first step in ensuring this data is ready to go is to go through an early assessment. This assessment asks a series of questions like, do we have enough data? Is the data even accessible? Can we get our hands on it? Is the problem we've been asked to solve actually solvable with the data that is available to us? And do we need to do a prototype to validate that? One of the biggest problems that I see with data science projects, as I said, is actually getting your hands on that data. Can we get it in? Can we use it? Is the data, in fact, on a hard disk somewhere on a closed system that we can't get access to? Is the data in a format that we can't even interpret? Doing an early assessment of the data will help us overcome those problems, or indeed decide that the project can't go ahead because of those reasons. After that, we need to start looking at the quality of the data. Now, we need to ensure data is or is not appropriate to the question being asked. If the data isn't appropriate to the question being asked, we can't answer that question. So factors such as completeness of data, or the time period the data is for, or even the relevancy of the data have to be asked. And that's where this stage comes in. And I should add on here that this is the sort of work which your data scientists can do, and they need some time setting aside for them to go through the data and start asking these questions. Next, we look at data preparation. The data preparation is where we get our hands on the data, we store it, we organize it, we clean it up, and we tag it. And these are all key elements that data scientists and data science communities and teams do. Getting the data, putting it in a particular form or format, getting it into a data lakes, organizing it so that it makes sense and it is consumable and that it can be accessed quickly, cleaning it out of any data that isn't relevant or erroneous data, and tagging it to make sure that to make sure the machine learning system actually can accurately recognize what that data is, more about that later, are all critical parts. And again, as I've said before, if you can't get hold of that data, it may be that your project needs to stop. But by making that assessment in the data phase at the beginning of the project, you can reach that conclusion without having spent too much money. Next, we need to assess the problem. Now, assessing the problem is where we start looking at what it's going to take to solve it. It's worth bearing in mind that experimental data science projects can take months or even years to complete. And I've certainly been on data science projects that have run for 18 months or more. So ensuring that we're asking the right question of the data and the right question for the business is pretty important. You don't want to get to the end of the project and find that you've built a model, but it doesn't actually answer the question we've been asked to solve. So this stage involves asking critical questions like, is the problem clearly articulated? Is there actually value in solving this problem? Is this the right problem for the business to solve, or indeed is it the right problem for our customers to solve? And importantly, can the problem be solved relatively quickly? If it is going to take 18 months, let's be aware of it before we get into it so we can ensure that we have sufficient funding for it. If it's going to be solved really quickly, brilliant, no problems at all. But if it's a big problem, how do we slice it smaller so we can release value on a relatively regular basis so the business can see the direction we're going and we can actually release that value to the customer and actually make sure we're going in the right direction? And the last thing we need to do is define accuracy. And as I said, we'll talk about that a little bit later on. But again, just to recap on it, if we're building a system that recognizes faces, we need to ensure that it recognizes faces accurate enough relatively often enough. So it might be that we set an accuracy level of 70% and consider that to be sufficient. If, however, we're talking about something like license plate recognition, then a 70% level accuracy probably isn't good enough. We need to be talking about 95 up to 100% accurate. So taking the time at the beginning of your project to actually define what that target accuracy is critically important, because it actually becomes your marker of done. If you don't know how accurate you want your system to be, how is it that we are able to say to the business, this thing is done, it actually does what it's supposed to? You could consider 70% to be accurate, but the business wants something much higher than that. So having those conversations right at the outset is critically important. Now, we said a few moments ago that data science begins with data. Well, if it begins with data, the next part is clearly science. And this that we're looking at now is the scientific approach. That is, you start off by observing the data. You then draw hypotheses of how the data could be used to answer a specific question. You then develop experiments that prove or disprove those hypotheses, draw conclusions based on those experiments, and make adjustments to your thinking and to your code, and then you repeat it again. And that fundamentally is the scientific method. However, with experimental data science, this loop has to be repeated for every single avenue that needs to be explored to answer the question that's been given. This means that you could be repeating experiments or repeating this loop many times before a usable model is landed on. Even then, many loops may be needed again to improve the accuracy of that model. And that leaves us in a position where we might be looking at something a little bit like this. This is a binary system. That is, for every experiment, there are only two possible outcomes, outcome A or outcome B. But the thing is, data science isn't binary. Nonetheless, using this as an example, you can see that just 5 rounds of experiments have led us to 31 different possible outcomes. And a data scientist could conceivably complete this number of iterations in 3 to 4 days. However, perhaps a slightly different system exists where there are potentially 3 different outcomes. Now, in this version, just 3 iterations puts us in a position where we have 36 possible potential outcomes. That's less number of experiments and a greater number of outcomes. In all honesty, though, data science is a little bit more like this. That is an unpredictable number of iterations and an unpredictable number of outcomes. And this is the reason why it's very difficult for a data scientist to estimate how long something is going to take. They simply do not know. They don't know how many times they have to repeat the experiment. They don't know how many different outcomes there could be from that experiment. And they don't know what experiment they need to conduct after those outcomes have been completed. So although they might be able to talk about the experiment they're doing right now, they might be able to talk about the potential outcomes for it and what impact that might have on what they do next, they generally cannot talk any further ahead than that. That means they cannot even predict their own work, and they cannot estimate their own work, because it is you're asking them to look too far into the future, and there are too many different permutations that could lead them in that direction. And that means that fundamentally, the data science approach, in this case, the scientific approach, in this case, the experimental data science approach, in this case, is not predictable. But Scrum relies on predictability to manage our work in progress limits. We do this through velocity. The velocity tells us how much work we can pull in every single sprint and how much work is going to get done every single sprint. If a data scientist is unable to tell us how much they're going to get done in 3 to 4 days, how are they going to be able to tell us what they're going to get done in a sprint? And this, by definition, puts us in a slightly difficult position. It means, fundamentally, Scrum does not work for experimental data science projects. But it does work for engineers, and it does work for ML engineers. So what do? What we do is we look at SCRUMBAN. That is, we take from Scrum the regular cadences, the transparency, problem slicing, reviews, and stand-ups, all the things that work very well for teams that are of any type, delivering any kind of project and working on any kind of problem. We then borrow from SCRUMBAN the key elements that are very valuable in this situation. Not estimating, not having an end of sprint commitment. If a data scientist is unable to predict what they're going to do in 2 or 3 rounds of experiments, they're not able to predict and make a commitment to what they're going to do for the end of a sprint. So we drop that element completely. We still maintain regular progress. We still maintain the capacity to review work when it's done. We also allow for the opportunity to present work in progress as well. So a data scientist is then in a position where they're not making a commitment for what they'll get done, but they are saying, I will show you when it's done, and I will show you my progress through the problem on a regular basis so you can see the value that I'm releasing, even if it's not necessarily a completely done thing. So how do we go about doing that? First off, we split the teams. We have one data science team and one ML engineering team. Both teams are working on separate parts of the problem. The scientists are working on the model. The engineers are building the APIs, the back-end data storage, front-end systems, and then any ancillary features that are needed. If you run both teams together, you can lose a lot of that transparency and a lot of that understanding. So splitting them out will really, really help them to focus on what they're doing. You'll also notice that by splitting the teams, you can use SCRUMBAN for the data scientists and maintain Scrum for the engineers. So we can use 2 different ways of working across the same project, which allows 2 different teams that operate in fundamentally 2 different ways to continue to operate in 2 different ways and not compel them to work the same way. It's also very, very important that we maintain a high level of alignment between the 2 teams. We'll talk about how we do that in a moment. By running 2 teams, you actually break their dependence on each other as well. They're able to operate independently, they're able to deliver independently. But that alignment remains absolutely critical. And we do that by having a one-team mentality. That is, we have one stand-up and everyone comes to it. The data scientists talk initially and then the engineers talk afterwards, each with their own board, each talking about the work that they are doing, but each listening to each other about the degree of progress they are making, because one feeds into the other. And having those conversations and keeping them broad and open means the 2 teams can support each other and head off any problems before they really occur. This also means that both teams have the same cadence, they share a review, they share a PO, and they regularly collaborate together. So for all intents and purposes, despite the fact we split the teams into 2 different teams and they operate in 2 different ways, there is in fact one team. They just have to have different boards and different methods. And this is critically important. This is how we maintain that tight alignment, but that loose coupling. In the same way as before, when we're talking about established data science projects, we will see that engineers have a higher rate of delivery than the scientists. And this means that their delivery, the engineer's delivery, can be impacted by the scientist's rate of progression. So we need a way to get around that. And this is it. What we do is we set up very early on an agreement on how the data model will work. That is, the data scientists say, this is the type of data we're going to be delivering to you. This is its form and its format. The engineers understand the data that's going to be provided to them, and they're able to build a system which is ready to receive that data. We're then able to set up a considered fake data approach. We know the data that's going to be provided. We know what form and format it's going to be, so we can go out and we can create something that matches that data structure. Obviously, as I said before, we have to ensure the data is appropriate and it represents the real world data as closely as is physically possible. But by having this approach, what we are able to do is separate the 2 teams and break their dependencies on each other. The data scientists know the end game in terms of what they're delivering, and they can build their data science model to follow that. The engineers know the data they're going to be receiving, and they can build a system that is able to receive that. And in this way, we decouple both the teams. Somebody will recognize this approach. It's the API approach we are seeing a lot more in engineering projects these days. It's just that same approach applied to a data science situation. The next thing we need to do is supercharge our transparency, and this is critically important to making sure that your teams operate well. And we do that by primarily having 2 boards. Both teams have different boards. They both attend the same stand-up, but what we need to do is ensure those boards represent what the project vision is. What is the direction that we're going on? If we've then gone and sliced our question down, which is highly likely in an experimental data science situation, to make the problem easier to solve, we need to get that current question up and get it on the board. We also need to ensure that unit testing is well defined and understood in terms of where it fits. And I say that because with data science projects, it is often in a different place. So when we do engineering, we do unit testing, we do a deploy, and then you UAT it. When you do data science, you can't test the work terribly effectively until it's been integrated. So a data scientist will do their work, they will check it, they'll test it as far as they're able, it will then get integrated, it will then hit a deploy, and then before you hit QA, the data scientists need a data testing phase, and then you can move into traditional QA. And that might look a little bit like this. And in this situation, we have two boards operating at the same time and presenting all these different elements. The data scientists have to do explore, build, test perhaps, and then ready for engineers. The engineers have there to do their work in progress, and then the data science testing, and then the QA, and then done. And critically, the value is only released when you reach done. So you could conceivably consider these two boards actually as one following on from the other, and it'd be one super long board, the data scientist blending into the ML engineering board. And you could represent it this way. I just haven't found a wall that's long enough to do that. So typically I keep them separately. Interestingly, we also have here what the current question is and what the vision is that we're trying to achieve. So the vision being the overall, the current question being a slice of that big vision. And there over on the right-hand side of the data scientist board, you see the current and the target accuracy to give an indication of where we have reached and where we're trying to get to before we consider this part of the model or this part of the problem actually done. Next, we need to start looking at setting up a business cadence. And this is really, really important. When we've moved away from Scrum into Kanban, then you aren't necessarily delivering on a regular basis, and that can unsettle businesses. They actually quite like the regular delivery that a Scrum can bring. They like being able to know in their diaries what they're doing from one week to the next and when they're seeing their teams and when they're not. So bringing that element into SCRUMBAN is very, very advantageous to the business. What I also find is that ML engineers need a daily stand-up, whereas data scientists 3 times a week is sufficient. They don't need to meet every single day because their experiments just aren't that fast-paced. They're fairly quick, but not fast enough to meet up daily. In terms of iterations, 2-week sprints, 2-week iterations seems to work very well with one planning cycle and one review cycle in each. And again, the whole team comes to planning and the whole team comes to the review as well. And lastly, we need to recognize that data scientists are a relatively new breed. It's fairly new to industry, it's fairly new in academia, and as a result, it's not fair of us to imagine that they're able to operate at exactly the same way or with the same skills as engineers, where software engineering has been going for 60, 80 odd years now. And as a result of that, we need to recognize that data scientists typically expect, from an academic perspective, from the training perspective, to sit on a problem for a year and work on it for a year and then deliver a solution at the end of that time. Obviously, that doesn't work for businesses today. That doesn't operate for the VUCA environment that we're in, and that doesn't work for an agile environment either. Their approach typically isn't very agile. So we need to help them to become more agile. We need to help them to be able to work on problems in a way that are able to deliver value more regularly. And that means we need to introduce new skills like collaboration, seeking good but not perfection, slicing a big problem into smaller steps. And these are all potentially new ways of working. And there are also things like peer review and code quality reviews, which are things that data scientists typically aren't used to, but that we know are critically important to deliver high quality solutions. Simply put, we cannot assume that data scientists have the same skills that engineers do. In terms of this little bit at the bottom, this picture over here, I've been asked to explain in a couple of previous presentations, so I'll just take a moment to do that. The question that we've been asked is this: is a person wearing the correct PPE? Can you build a machine learning system that can assess that question? That is a question that data scientists could sit on, and they could sit on it for a year or 18 months to try and answer. Actually, it's more advantageous if we're able to break it down to small steps. So assuming we've got a video feed that we're trying to analyze, the first question might be, is there a person in this feed? If there is a person, can you identify their upper body and separate it from their lower body? Once you've identified their upper body, can you identify the PPE that they are wearing on their body? And lastly, can you critically recognize that the person is wearing a respirator? Each of these becomes individual data science models which recognize different parts of the problem, and then when combined all together, actually solve the problem. Is this person wearing the correct PPE? And in this example, you can see I've set a line of a target accuracy of 70%, 100% accurate being on the right-hand side. And in this graphical representation, you can see each of those data science problems, each of those machine learning models slowly progressing towards that target of 70% accurate. But no one of them is there yet, and they're all at slightly different stages. So what we're representing there is how a problem might be sliced by a data scientist who, from an academic perspective, would just work on the master question. Instead, by cutting it smaller, we can work on smaller parts of the question and actually recognize our progression much more easily. So that's everything that I need to cover for the moment about experimental data science. So let's take a moment just to start considering the differences between data science projects and software-led projects. The critical ones are these, and I'm going to take them all individually and then talk about them a little bit. When we talk about model training, and this is a term we'll hear very regularly when we are talking both about experimental data science and about established data science. It's just that with established data science, the model training has already taken place by the time you receive the model. With experimental data science, it's actual piece of work that needs to be done. Broadly speaking, the way it works is this. You get a bunch of data and you tag that data to describe what it is. In this case, it's cat data, and I'm saying all of these pictures represent cats. You then feed that into the machine learning model, and it starts to learn what a cat is. And eventually you'll come to a point where it says, this is a cat. You put in a picture of a cat, it says, this is cat. Brilliant. Well, kind of course it would. You told it was a cat, you tagged it with cat. So to validate it, what you do is you take a variety of images that have not been tagged as cat and are questions, and you feed those into the data science model, and it should be able to, if it's working and performing to a high enough level of accuracy, say, this is a cat. Bear in mind that for a human, recognizing a cat is very easy, but a cat might be sat up, it might be lying down, it might have its tail up, it might have its tail down, it might have its legs tucked in, it might have its ears back, facing forward, facing back. So all of these actually make the recognition of cat very difficult for a machine learning system, although very easy for a human. So training the data, training the system to recognize all those different permutations of cat is what model training is all about, so that it is able to recognize cat from any angle, standing, sitting, lying, etc. Next, we have model accuracy. We talked about it a little bit up until now in the course of the presentation, but let's get into a little bit more depth. There are three parts to model accuracy. Model accuracy measures how performant a model is. That is, how well it is performing the task that is being asked of it. And this is often measured using a mathematical formula called R squared. There are lots of other ways of measuring it, but this is one of the most common. And this takes account, or this model takes account of how far the model is deviating from what is correct. And it takes account of both right and wrong, but also true negatives, true positives, and false positives and false negatives. As a result, it's way more complex than I need to get into in this conversation. But the point is, there is a mathematical way that data scientists are aware of to measure the accuracy of their model. Next, we have minimum accuracy, and this defines the minimum performance level that business is prepared to accept. And the target accuracy and minimum accuracy may be one and the same thing, but it's worth having the conversation to ask, what is the lowest level? How do we know when we are doing good enough? You still may want to go further, but how do we know we're doing good enough? And the business can then choose to invest more in getting better up to their target accuracy, but what is the minimum level they are prepared to accept? Obviously, this implies that target accuracy is the ideal level of performance the model needs to hit. These all need to be considered. They all need to be considered and agreed at the outset. Having this conversation 3/4 of the way through the project is way too late. And it's way too late for this reason. Accuracy relates to value and cost. That is, the more accurate a model is, the more valuable it is. However, chasing a target accuracy will lead to a longer duration and a greater cost. Because if your accuracy is, 60% and your target is 80%, you need to invest more money to increase that level of accuracy. However, chasing a target accuracy can also lead to rabbit hole mentality, and it can lead to us spending more money to build up that level of accuracy and spend more money, and that spend may not necessarily be the best use of that accuracy. To avoid that, what we need to understand is the value of percentage increase in accuracy. That is, how much do we need to pay per iteration, per sprint, to improve the accuracy, and how much accuracy are we likely to get by that investment? If we use that typical example of a facial recognition system, we may want to target an accuracy of 70%, but find that we're delivering at 60%. And if we were only improving by 0.2% per iteration, we're going to need an awful lot of iterations in order to get up to that 70%. That may actually represent a poor investment of the budget, and it may be decided that 60% actually is good enough. Let's move on. However, if we're talking about an industrial plant where 0.2% improvement equates to $2 million of accrued value, suddenly it might actually be worth investing that same amount of money into another iteration to get that extra 0.2%, 0.4%, 0.6% improvement. And the point is that targeted minimum accuracy can be used to have a conversation about when to continue and when to stop improving on a model. And by having these conversations, having this data available, it means that we're able to have those conversations in a less emotional way. We're not reliant on the data science and saying, hey, can you get it a bit better next sprint? Yeah, I can. How much better do you think you can get? Oh, I don't really know. By having these conversations, having these targets, having this data, we can actually make that conversation much more objective and much more informed, and then make the relevant decision about whether we continue making improvements or whether we stop there and move on to another part of the project. I did say that we would come back to model drift and detecting drift. And to start with, I'm actually going to read out these definitions. These are the official definitions, and I can't sum them up better than this. What is model drift? Model drift, also known as model decay, refers to the degradation of a model's predictive power due to changes in the environment, and thus the relationships between the variables. That is, when you get a model into a live situation, it will, over time, degrade and get worse at making predictions. If it is going to do that, we need to have a system in place whereby we can detect that drift. Drift involves statistical change in the data. The best approach to detect them is by monitoring its statistical properties of the model's predictions and their correlation with other factors. That is, we need to have some sort of statistic in place that is able to detect our drift. We talked about that a few moments ago. It's R squared. It is whatever method, whatever number you are using to detect or to track the accuracy. So detecting drift is very much a question of saying, well, how far are we away from that target accuracy? Our target accuracy was 70%. We went live with 70%, and 6 months later, we're now only achieving 60%. Well, we've detected the drift has happened. We now need to do something about it. And that do something about it is retraining the model. This is very, very common in data science systems. You have a model, you train it, you put it live, and periodically you retrain it on live data to ensure you achieve high levels of accuracy. And that takes us very neatly to actually how you go about releasing data. So how you go about releasing your model. And when we're talking about a software engineering system, actually, you've only got one release. It is the live release, effectively. But when we're talking about data science, we have several different ones. We have the alpha release. This is where we release the data into the live world and we test it for accuracy using live data with real users in the live environment. This is going back to the example I talked about where we move from the office environment to a live environment and suddenly we find the cameras are in a different place. Or if we're talking about a different type of data science system where we are moving to a live environment and suddenly our users are using it in a way we didn't expect or a way we didn't predict. And as a result, the model doesn't work. And we go into alpha release expecting the model not to work. We're expecting it to have a big hit in performance, for it to not perform the way we expected it to. And that's why we mark this as an alpha release. And it's there to protect ourselves and to say to our customers, say to our clients, we know it's not going to work as effectively as it did in a lab environment. We need to get it out there and see what it's doing and how it's performing so that we're able to then make some changes. You make those changes and then you hit the beta release. This is our effective first release. This is where we are putting it back into a live environment and we're starting to check for what the degree of drift is because we're expected to be far, far less. We can then retrain and re-release. Once it's out there, we then need to hit a period of run and maintain. That is cyclical check-ins to test the model for drift and accuracy. And whereas when we do normal software engineering releases, we release it and we typically say to our client, hey, that's it, off you go. If you get some bugs, send them in, and if we've got a support contract, we'll fix them, and if we don't, then you need to pay for them. In this case, we actually expect there to be drift. We expect the accuracy to decay over time. So we put in place a system whereby we make regular checks on that drift and then retrain the system to do it, to handle that drift. And if you're working with an effective machine learning platform, those can actually be done automatically. A system can be built whereby the degree of drift is checked on a regular basis, and automatically new training systems are put in, are spun up, and the system is retrained on live data to try and close that down, and only comes back and contacts the data scientist if it's unable to improve its accuracy enough. But the point is that run and maintain strategies need to be considered and need to be put in place to ensure that the system performs the way we expect it to. So to conclude, we have an established data science approach, and the established data science approach is one in which we're working with known problems, where we need to agree the degree of accuracy upfront. We need to agree which data models we're using upfront, and agree within ourselves, with our data scientists, our ML engineers, what the data looks like, and we need to run a data preparation phase. Scrum works, but we need to maintain alignment between the components within our Scrum team, between the disciplines within our Scrum team, to ensure they are consistently and continuously aligned with our users and with user stories. We need to be aware that not doing this and having stories that focus more on the disciplines will lead to delays in value. And we need to plan for drift and retraining, because even with a pre-established model and established data science system, we're still going to be in a situation where there will be drift and retraining will be needed. When we're talking about experimental data science systems, we are, we are talking about working with new models or emergent models. We're talking about experimental data science and experimental approaches, and those being inherently unpredictable. So SCRUMBAN is a good way of resolving that issue. To do that, we have to have two teams, but those two teams operate as one team and they deliver as one team, and we need to agree our accuracy up front. As well as that, agreeing what our data models are and how the two teams interact at the data level is highly important, as is running a data preparation phase, in order to be able to understand if our data is appropriate to the questions we are being asked on. Upskilling our data scientists and helping them to grow and improve their skills is critically important, as is being awareness of delays to value and using fake data and the API approach we discussed earlier to overcome those. And be aware that you have to plan for drift and you have to plan for retraining. And at just over the 1 hour mark, we are done. Thank you very much for listening. Greatly appreciate you taking the time. If you have any questions or queries, I'm happy to hang around for a little while and answer any that you've got. If you want to contact me directly, you should have my details. If not, I'll put them back on the screen in one moment, and you can reach out and ask any questions or queries that you have if you want to. And there is my contact details. Thank you all very much, greatly appreciated. Does anyone have any questions or queries? Oh, sorry, do go ahead.
Hey, Chris, that was a great presentation. Thank you so much. This is Sahib from Scotland.
Hey there, nice to hear from you. How are you?
Thank you so much.
My pleasure. Anybody have any questions or queries they want to put out?
Yes, there's a question on the chat from Nawaz. It says, is the work flowing downstream from data to engineering team all the time? Is there a situation where the work go back as well? Maybe
okay.
Complete missed details. How does it affect practice?
Yep, most certainly, yes, absolutely it can do. So if you remember, we were talking about how QA is done, how testing is done as a data scientist, and that it doesn't form a part of the data science mainstream of work. It can only actually be done once a data scientist has completed their work and it's been integrated into the overall system. And then there's a phase of data science testing which falls after the code has been completed, after the pull request is done, but before traditional QA and UAT. And that's the moment where a data scientist is able to test their work actually integrated with the system. And that's the point where it could loop back to the beginning of the data science stream because there's an error in it. Now, that is a little bit waterfally. So we have to be super careful about that one. And the way we achieve that is by slicing those tasks down into smaller pieces using that image that I suggested. So again, by way of example, the first the question was, is an individual wearing PPE? The first question is there a person in the screen? So if we had a live feed of a video, we're actually asking the question, can the system recognize a person on that screen? Now, because we're asking a question, we also have a target accuracy. Let's say our target accuracy is 70%. So by having a small question that is more easily achieved, we're reducing the risk of having to loop around again. So we have the data scientists, they do their test, they build a model, and they say, what level is this model performing at? And it's a simple slice of the overall question. We're at 10%, let's loop it again. We're at 20%, let's loop it again. 30, 40, 50, 60, 70. We've achieved 70%. It's now we now have confidence this model is good. Let's release it into the engineering solution and then test it once it's been integrated and once the pull request is done. But because they're putting a model in that they have a high degree of confidence in, the likelihood of looping back is relatively low, or it's only likely to happen because suddenly we've lost a few percentage points we weren't expecting to. But because the model is a simple model and we've been able to take a slice of the overall problem rather than try and solve the whole thing, the low degree of risk is much, much lower. And as a result, we're operating in a much more agile way. Does that answer your question? Noaz, if you want to, please feel free to come off mute and ask me for a little bit more detail.
Okay, thank you.
All right. Yeah.
Sorry, I have a question. Just
sure.
Is there any matrix or any other way you can see how teams are performing? Like, you know, we have to be predictable. So I understand that research teams cannot be predictable, but we have ML teams. Is there any matrix from where we can prove how teams are doing, or you know, how we can see the
Yeah, no, totally get it. So we're borrowing from Kanban here, and there are certainly ways in which Kanban can deliver those predictability metrics that you're talking about there. The best one that I'm aware of is Actionable Agile Metrics, which is a system that looks at how fast a team are working historically, how much throughput have they got, what's their cycle time of their data, and these are all the sort of metrics you expect to see when you're working in a Kanban system. So rather than using a Scrum method prediction where we're trying to say how big is big and how complex is these individual pieces, then we're going to use instead looking at how quickly a team is able to progress and on average how quickly they're able to deliver work, and that will help with those metrics of how fast the team are going, when they'll be able to deliver stuff, and how quickly they're able to deliver stuff. And one of the critical reasons of using that is not only is data science unpredictable, but the way in which you could try and predict it is also unpredictable. Here's an example as to why. When we're trying to use relative estimation for a software engineering piece, there is a rough correlation between degree of time and degree of complexity. The more complex it is, the more time it takes. And the less complex it is, the less time it takes. Yeah, we may use Fibonacci just to say more time is significantly more complex, but there's still a relationship there. Even in Fibonacci, there's a relationship there. It's just a complex mathematical one. When we're talking about data science, that relationship is not necessarily there. We do have a situation where it's entirely possible for a simple task to take a very long time.
Exactly. Yeah.
Exactly.
And that's why, like when you're doing one piece of research, it might take different time than the second type of research, right? So that's
exactly.
You collect the data. It's not actually predictable, right? So
exactly. So because we're following a scientific approach, it is not predictable at all. However, there is some complex math that will actually allow us to predict it. And I would strongly recommend you do take a look at Actionable Agile Metrics, which was produced by a chap by the name of Daniel Vacanti. And because it works with averages, so an average sized piece of work, it discounts the need for how big that piece of work actually is. And over a period of time, it can help you to predict how long it would take you to deliver an average cycle of work. So if you're talking about a data science experiment, and a second data science experiment. Although the two are different, averages can be drawn between the two. And the work done by this gentleman, Actionable Agile Metrics, helps us to understand that. And that's not just data science based, that's about any Kanban project at all.
I get it. Yeah, that's exactly what we are using currently, the actionable agile.
I've used it a lot, great faith in it, and it is absolutely the right way to go.
Yeah. By the way, Chris, great session. Really
Thank you very much. I'm glad you liked it.
Thank you.
No problems.
Okay, Chris, you have another question from Matthew. It says, have you ever tried to form one team with DS and ML engineer?
Yes, I have. And the work you've just seen is the outcome of that. So like every other Agilist, when I was first given a data science team, I said, hey guys, let's do Scrum. Yeah. And it didn't last very long. It didn't work. And like everyone out there and all the things you read on blogs, data scientists very quickly said, Agile doesn't work for me. I can't work this way. This is wrong. This does not work for me. And rather than the typical approach of saying, well, we're Agile, we're Scrum, you will work this way, I took the time to start investigating why and what the problem was. And the outcome is literally what you've seen. It turned out that this was an experimental data science project, and I was trying to make experimental data scientists work in a Scrum fashion. And that learning led to the SCRUMBAN approach and over time and refinements, the information that I've given to you guys here. So that the critical point is recognize what type of team, what type of project you're working on, and then pick the approach that is right. If it's an established data science project, Scrum works just fine. And I'm working with a Scrum team right now that is doing working with established data science models. If they're not established data science models, if they are in fact experimental data science models, then you need to switch over to SCRUMBAN. Otherwise, your data scientists are going to start squealing and be very, very unhappy. But more than that, you're not going to be able to deliver in a predictable way, and the business is going to start squealing and getting very unhappy. And suddenly all things get started pointed at the data scientists. These guys are not delivering. These guys can't predict what work they're doing. These guys aren't able to give us what we need. And suddenly we're in a position of conflict when actually the problem isn't how data scientists work, and the problem isn't Scrum and Agile, it's the fact that those two just don't fit together. Instead, a different approach is needed.
Okay. Another one says, why do we need two boards? Wouldn't it be possible to merge into one?
Yeah, absolutely. And it could, you certainly could do. It would just be a super big, massive, long board, because the data scientists operate in a different way to the data engineer. So a data engineer, typically to do, in progress, maybe QA and done, to 4 columns and that's it. Whereas the data scientist may actually need data cleaning and cleansing. They may need some data reformatting. They may need model experimentation. They may need model selection. And those series of steps actually making it more transparent, making their work more transparent, but also a form of value stream mapping that helps them to understand where their bottlenecks are. And the point is that both teams operate in slightly different ways. We're talking experimental data scientists here. Both teams operate in slightly different ways, and as a result, 2 boards actually makes their work more transparent. If you try to merge it together, what you actually find is you end up with a board that doesn't work, or work that jumps between different columns and skips over columns. If, however, you're dealing with an established data science project, 1 board is absolutely fine. It's strictly when you're talking about an experimental system that 2 boards actually works much, much better.
Thank you. Another one says, how long does it take on average for engineers to acquire the skill and agile mindset?
Thank you very much. Appreciate the translation. I pretty much got the gist of what it was, but didn't have that degree of translation. God, there's a question. So this one specifically asks about engineers. I'm going to assume it was meant to be data scientists. So engineers, I'm finding more and more engineers have an agile mindset. When I work with them, agile is taking a far higher level of precedence. So many are coming in, having had some level of training. It actually becomes a point of refining some of the nuanced techniques. So starting to talk more about how we can improve, starting to talk more about how we can build up psychological safety, how we can work on a team emotional intelligence. So that's the engineering part. When you're talking about data scientists, then we're talking about a way different question, because a lot of these folk have come from an academic background, because a lot of these folk have come from a position where they work on a single data science project for a long period of time, and people aren't asking them to work in a different way. And so the transition can actually be an awful lot harder. And it depends fundamentally on the individual and how open they are to change as to how well they're able to change. That also actually reflects how effective they are as data scientists and how long they might exist in an organization. So I've worked with one set of data scientists who are quite young, and they were quite bright-eyed, and they were quite open to new ideas. And it took them sort of 2 or 3 months to pick up the new skills. But even for them, peer review was a totally alien concept. Slicing problems small was a totally alien concept, and I needed to work with them and do a lot of games and a lot of agile practice to get them to a point where they were actually starting to understand the value in what they were doing. I've worked with another data science team where the data scientists are a little bit longer in the tooth. They've been in the business for a lot longer, but almost as statisticians, more so than data scientists and hardcore mathematicians. And their desire to change is way, 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 way less. So for me, it's a question of pick your battles and try and work as effectively as you can with the individuals in question. What I find actually works is when data scientists start saying, this doesn't work for me, help me out, Chris. Great, I can step in. They're then in a mindset where they're open and ready to try different things, and then it's a lot easier.
Yeah, Chris,
Thank you very much. One more says, have you ever faced a situation where data scientists could not deliver agreed level of information within sprints, and how was it addressed?
Okay, I heard a voice on the line there, so I'll answer this question, then let's have that voice. I don't want you to be left out there, sir. Okay, so have I ever been in a position where data scientists have been unable to deliver their work in a sprint? Oh, goodness, yes, absolutely, definitely. But that's where the SCRUMBAN thing comes in. So you actually build a working relationship there and working agreements where you say you do not need to deliver a done thing at the end of each sprint. What in fact we want to see is your progress or a done thing. When something is done, you show it to us. If it's not done, tell us how you're getting on. Show us what you're achieving. And data scientists are actually able to do that. They're able to put up graphs and charts that show how far through a piece of work that they are getting, or what degree of accuracy they've got, or whatever metric you want to use. So this is very much a question of working with your data scientists. And this is the reason why stepping away from Scrum can sometimes work really, really well, because they are not compelled to commit to something being done. You say, what have you gotten done? Or how far through are you? Please take us on the same journey that you are. And by doing that, you reduce the pressure and improve data scientists' capability to deliver on their work. And it can be over several sprints they're delivering. But critically, this is where you start slicing their problems down and helping them to slice. They're not used to the idea of making a problem smaller. They're used to solving a whole single problem. And when they're working in that mindset, 2, 3, 4, 5, 6 sprints is not untypical. Obviously for us, that's bad. Obviously for releasing value, that's bad. So trying to encourage your data scientists to change those skill sets, look at the problem in a different way, helps reduce those timescales down and reduce their deliveries down to a much more reasonable way. And obviously, as you can imagine, by working on a smaller problem, then you can actually get to where you want an awful lot quicker. I heard a voice on the line. Would you like to ask your question again, sir?
Yeah, that's me, Chris. My name is Samuel.
Hello, Samuel.
I've never worked in a data environment before, but you did mention something earlier on about the fake data, the weekly data. What's it called? The weekly, weekly data, the one that you gather together, and the real life. I just want to know: is there any way that the weekly one that you actually just got might affect the project in whole, or the weekly one and the real data has got something in common?
So for that particular example, if I don't answer this quite right, please correct me. For that particular problem I was building, my team were building a data science system for an industrial plant, and getting the data just wasn't possible. The data was in a closed system. We couldn't get it at all. To get the data, we actually had to implement an on-premises solution, then we'd have access to the data. This doesn't help us build a system. This doesn't help us test a system or train a system. So instead, we were able to get 12 months of data, but from 2017. So the data was real, it was accurate, we could train on it and we could use it. It was just a couple of years out of date. So we exported that data, we had it brought over to us, we put it on our system, and then we used it. So it wasn't quite weekly, but because we had 12 months of data, we could actually grab 1 week's worth of data and say, we're just going to check and test or train on this 1 week of data. So it was a fake data approach. It's not the live data, but it was as accurate a data as we could possibly get. If we try to create our own version of that industrial data, as we often do when we're doing software engineering projects, we've all been there. We create a database, we just put whatever nonsense in there we want, because it doesn't actually matter. It's what we can get out of the database and present on the screen. Fantastic, it works, no problems. You can't do that with a data engineering. Sorry, you can't do that with a data science problem. You have to have data to work with. It's close to accurate, as close to real as you possibly can. Otherwise, you'll be training on rubbish data. It just won't work.
Thank you so much. That really answered my question. Thank you for a wonderful, insightful presentation.
Thank you, Samuel. That's very, very kind of you.